So then I'll be back Thursday.
Okay.
Okay. I hope you can't hear that noise. Do you hear all the noise near me?
No, not at
Okay. It's very noisy outside, but okay. Hello, Thomas.
all. Hello, Thomas. Okay, Christina, you may start whenever you want. So
All right.
to give you the host.
Okay, so I apologize if anyone can hear this. A lot of noise outside my home right now, but so this is the second lecture, and today I'm going to go over open problems on scalar curvature. So if you didn't attend the first lecture, you'll be fine. So recall that the whole lecture series is intrinsic flat and Gromov-Hausdorff convergence, and we talked about many notions of geometric convergence in lecture 1. We reviewed CK-C0, Lipschitz, and Gromov-Hausdorff convergence, the Sormani-Wenger intrinsic flat convergence, which has two different notations, SWIFT or a fancy F, and volume preserving intrinsic flat convergence. And then we also mentioned the Allen-Perello-Sormani's notion of volume above and distance below convergence, which we'll discuss further today. Again, many of the open problems consider these last two notions of convergence, so I'll review them some more. We're going to consider three-dimensional manifolds with scalar bounded below by H. H might be positive or almost non-negative, but very close to 0. We won't really be considering too much scalar greater than or equal to -1 or anything like that in this lecture. And their limit spaces. Now, these limit spaces under volume preserving intrinsic flat convergence are our primary concern. We're interested in which geometric properties of MJ3 with scalar greater than or equal to H will be conserved under this convergence to limit spaces. As many of you have been attending Mondino's lecture, you know about the properties of Ricci curvature that persist under measured Gromov-Hausdorff convergence to their limit spaces, which are CD spaces and RCD spaces. And here we don't have the possibility of having Gromov-Hausdorff limits due to many examples. So we're using this weaker notion of convergence called the intrinsic flat convergence. But we're not hoping for too much from intrinsic flat alone, as we will see in a number of examples today. We're going to really need volume preserving intrinsic flat and this particular notion of convergence, which is a little bit stronger. Which rigidity theorems hold for M3 with scalar greater than or equal to H have geometric stability? Now that's the kind of question that says, is the rigidity theorem sort of true in some sense? In the limit case, if MJ almost has the properties of the rigidity theorem, is it close in the intrinsic flat sense to the exact specific manifold it must be in the Riemannian setting? And Many of these conjectures are inside the survey conjectures on convergence and scalar curvature that I wrote with my fellow participants at the IAS Emerging Topics meeting. Lectures 3 and 4 will concern techniques to apply to prove convergence. So they will cover the techniques that you're going to need in order to prove the various open problems I will be mentioning throughout today's lecture. You can find these in this website, which I included and shared on the chat. All the different papers that I will be referring to. Okay, so let's talk about open problems and scalar curvature. We're going to consider MJ3 with scalar gradient to H and their limit spaces M infinity. The MJ3 might not have Lipschitz or Gromov-Hausdorff limits, so we're going to consider the Swift limits and volume preserving intrinsic flat limits. And here's a classic example to keep in mind. This sequence here has a volume preserving intrinsic flat limit. It does not have a Gromov-Hausdorff limit because the number of wells is increasing. But as long as the total volume of these wells is going to 0, we will still have a volume preserving intrinsic flat limit. And I also include this loops here because these are kind of important to many of the examples. Loops that also become thin, and if their volume is going to 0, will disappear under intrinsic flat convergence. But the length of the loop may affect what the limit is. So we're going to see some examples where the lengths of these extra tunnels or loops running around will affect the actual distance function on this limit space. In this case, the loop is longer than the direct distance, so it does not affect it. This picture, the limit space, is actually a three-dimensional sphere, standard one. Which geometric properties of MJ3 with scalar gradient to H are going to persist on their Swift and volume preserving intrinsic flat limits? Since MJ C0 converges to M implies that MJ volume above distance below converges to M, implies that MJ volume preserving intrinsic flat converges to M. We can use this, in 1 second I'll answer the chat. We can consider which geometric properties persist under C0 and VADB convergence as well. Let me just glance at the chat.
Yeah.
H is a real value, yes. Scalar curvature is a real number, so H is a real value. However, we're mostly going to be considering H0 or positive. So since these two notions of convergence imply the one that we're most interested in, you can consider which geometric properties persist under C0 and VADB convergence. And many of them have already been checked under C0 convergence. So I will discuss the results that have already been shown for C0 convergence, but the questions involving volume above, distance below convergence are almost completely open. Okay. So let's quickly review these notions of convergence so you can remember what they are. Volume preserving intrinsic flat convergence means that you're assuming that the volumes converge to the volume of the limit space. The volume of the limit space was measured with a weighted sense that I discussed yesterday, and we'll discuss more on the 3rd and 4th lectures. And the other requirement is that the convergence happens in the intrinsic flat sense as well. And remember that the intrinsic flat convergence happens if the distance in the intrinsic flat sense goes to 0, where this distance was taken over all complete metric spaces Z of the images of the two manifolds into the common space Z over all distance preserving maps into the common space Z. So you have your M1 and your M2, they go into a common space Z. This is like Gromov-Hausdorff, but after you get into the common space Z, you measure the distance using the Federer-Fleming flat distance, which is a measurement that asks for a volume of this yellow region whose boundary should equal the difference between these two plus a little extra piece A, which is the same dimension as the sequence. So as long as there's only thin extra things sticking out and there isn't too much volume between them, this distance can be quite small. All right, so we have this that I've already mentioned. I'm going to sort of keep the color coding here. CK is purple, C0 is dark blue, VADB is teal, and this one is whatever color it is. These are different colors. Anyway, CK convergence means you have these functions that pull back the metric tensors to G infinity, and they have CK convergence. That includes C0 convergence. The C0 limits can develop a conical singularity. And volume above, distance below convergence only requires that the volumes converge and that there's a diameter bound and that you have lower bounds on the distance. So it's not two-sided like these two give you two-sided bounds on the distance. Now you only have the distance below and volume coming down from above. And this gives you a Swift limit or a VADB limit in this case. The nice thing about this notion of convergence is it's rather easy to study. It doesn't require a deep knowledge of geometric measure theory. Anyone who's a graduate student can start immediately with asking questions about what can I know about a sequence of manifolds if I assume M infinity is smooth, and I assume that the MJs go to M infinity in this process. So these are relatively easy notion of convergence to start studying. And then ultimately, we have the volume preserving intrinsic flat distance, which requires both the volumes to converge and the Swift limit. So another thing that becomes easier to study if you don't want to worry so much about the full rigor needed to understand intrinsic flat convergence is you can study whether volumes are converging. A lot of these questions are still open even for volume convergence. And remember that volume preserving intrinsic flat and Swift convergence do not require that there's actually a diffeomorphism from M infinity to MJ. So it's much harder actually to sort of set up what you know about the sequence without having such a phi j. However, there are theorems that we're going to learn in the third lecture, which do allow you to show volume preserving intrinsic flat and Swift convergence without too much expertise. All right, so let's talk about the volume limit definition of scalar curvature. So I'm just getting into now, what are the properties of scalar curvature that we can hope will also persist on the limit spaces? So if you have a compact manifold Mg with the C0 metric tensor G defined by this distance, defining the distance here is infimum of lengths of curves, then areas and volumes can be defined using the Hausdorff measure. So this sort of thing can be defined also. Hausdorff measure exists on limit spaces. So we have a Hausdorff measure. And we have a diameter as the sup of the distances here. Has to be less than or equal to delta here when we cover each set U with a number of UJs that cover it up. Each of the diameters of UJ is less than or equal to delta. We take the sum of them to the n power, j equal 1 to infinity times Cn. And this is try to find an efficient covering. And then take the limit as delta goes to 0 so that your UJs are getting smaller and smaller as they cover U. And this gives you the Hausdorff measure, dimension n, for a Hausdorff measurable set. The scalar curvature can then be defined as long as you have these notions. Distances, volumes, areas are defined. Hausdorff areas will have the n change to be whatever dimension you're interested in the measure being. And so we can define scalar curvature as a limit as r goes to 0, 6, n plus 2, volume nr. This means the volume of Euclidean space of dimension n, a radius r ball, minus the volume VPR over r squared VNR. So this is a kind of second derivative of volume comparison to Euclidean space. Scalar curvature is also defined as the trace of the Ricci curvature, but that involves taking second derivatives, and that involves using a Ricci tensor, which involves having a notion of an inner product on the space, as well as having a metric tensor. So the scalar curvature is very hard to define on limit spaces if you don't have all that extra machinery. So instead, if you define it this way, which agrees with the definition defined the other way, you are not involving anything other than distances and volumes. However, it's still a second derivative, just like Ricci curvature is a second derivative, because we're talking about a limit here, which when you run L'Hopital's rule ends up being a second derivative every time. This is at least a second derivative involving volumes instead of a metric tensor. So a flat three-torus whose small balls are Euclidean have scalar curvature equals 0, and the standard three-dimensional sphere has scalar curvature equal to 6 everywhere. Easy to compute using this. And Gromov asked if MJ3 have scalar greater than equal to 0, does M infinity have scalar greater than equal to 0? To admit, Gromov is unsure. When he made the statement, it was not yet clear what way he would require MJ3 to converge to M infinity, and that was part of the question. In what way should MJ converge to M infinity so that one would still have scalar greater than equal to 0 in some sense on M infinity? So let's talk about a lot of examples, because after Gromov's question here, there were many examples constructed to deal with trying to show that maybe this is not even true. And that was the first thing that went. Sort of like this was a conjecture that was very vaguely stated. And the first way it moved forward was studying C0 convergence. Gromov did quite well with C0 convergence, and Bamler also has results in C0 convergence that I'll mention later. But in terms of studying other kinds of convergence that are weaker that would exist, since Gromov-Hausdorff convergence and C0 convergence doesn't always happen when you have sequences with scalar greater than 0, many counterexamples were brought up. So I'm going to spend the first half of this lecture showing counterexamples in some sense to how bad M infinity could be. So let's first look at Schwarzschild space and Illman and Wells. So you have the scalar curvature definition I already told you. And this is the Riemannian Schwarzschild space. So I just want to talk about this space a little bit because we're going to be using it a lot. Schwarzschild space was actually found, it's a black hole. It's the Schwarzschild black hole when it's space-time, but this is a Riemannian version, which is just a single space-like slice of the Schwarzschild space-time, which is the black hole space-time that everyone's heard of. This is actually a parabola here that is rotated spherically. So you have to realize that this is approaching flatness quite rapidly here. So this is Schwarzschild space. It has a parabola here, and it's rotated about a sphere. And this has scalar curvature exactly equal to 0, and it is found by solving for scalar curvature equal to 0 in a rotationally symmetric warp product and solving for the functions that would exist. And the only functions you get are Euclidean and various rescalings of Schwarzschild, where you have thinner and thinner necks here. This level set here is a sphere, and it is a stable minimal surface inside this manifold. Now, given that these Schwarzschild spaces existed and they've been known about since like 1918, what one can do is you can take a sphere, so this is a three-dimensional sphere, and you can cut out a ball in red here, and you can sort of glue in a Schwarzschild. And I can cut out this ball to be very, very tiny ball cut out. And if I glue in the Schwarzschild when it's a very tiny ball, I would scale the Schwarzschild enough so that the curvatures match here. You see, you want this to line up and match. Since this is a parabolic curve here, you can match it even if it's almost flat. So you put in this little Schwarzschild piece, and then once you get to here, to the stable minimal surface, you could attach a cylinder. Now a cylinder has positive scalar curvature because you have two directions here of S2 cross an R, and you can see you get the positive curvature from the S2 direction and 0 curvature from that direction. You average it over and you get scalar as positive. And then you can cap this off. Now this is not a C2. This is not C2 yet. One way to make this a C2 smooth manifold would be to run Ricci flow for a second, or you can just smoothen it by hand. Either way, this thing can be created. If you smoothen it a little bit, this part will even have positive scalar curvature. Every other part had positive, and then the blue part was the only part that had been scalar 0. So that part can have positive. And in this way, you attach those wells I was talking about. That's where I was mentioning the Illman and Wells. So you get the sequences I mentioned that Illman had, where there were increasingly many wells. Each one of these is you're cutting out little balls. You're attaching like Schwarzschild little necks here, and then you attach long cylinders and caps. You can cut out as many balls as you wish. They can be as tiny as you wish. You just have to scale the Schwarzschild more and more in order, using the parabolic effect, so that it fits in. So that's Illman's example. And these are actually also physically interesting. This could be, instead of being a black hole, you smooth it a little more. There isn't actually a horizon over here. This is actually the gravity well caused by a very small, dense planet or neutron star or something of that sort. And it doesn't break and create a black hole. Let me see what the chat is saying. This is essentially Gromov-Lawson's construction. Ta-da! It was a very timely chat. Okay, so Gromov-Lawson Shanyow tunnels are based on this idea. I was just giving the history that comes back from the 1918 sort of time period where the Schwarzschild thing is. So the main idea is that the Gromov-Lawson Shanyow tunnels are effectively the same as this, same as Schwarzschild pieces being attached between things and smoothed out. But they didn't have the Ricci flow smoothing out method, so they disconstructed them explicitly. All right. All right, so now the main point that Gromov-Hausdorff and Chaigneau made, they have this attached to this. So now they take the same kind of idea and they attach it between, say, two spheres. And then you can attach it between many spheres. Now, in this particular picture that I had here, which I brought up earlier in this course in the last meeting about how you can get really complicated limit spaces, notice here that the tunnels are getting different lengths. And you can make the tunnels have different lengths by putting cylinders of different lengths inside this tunnel region. And since the Schwarzschild part can actually be made arbitrarily small, you really can glue things with different lengths imposed as desired. Exactly. The Schwarzschild part doesn't contribute so much as the cylinder part. So the Gromov-Hausdorff tunnels can be glued between spheres of S3 to create connected sums of spheres with scalar greater than 0. And this was viewed more as a topological result when they discussed it, but I really want to emphasize the geometric side of it, because to us, it's important what lengths and distances are. So it's really important that we can actually make tunnels of different lengths running between things. All right, so Gromov had asked if MJ has scalar greater than 0, does M infinity have scalar greater than 0? And suppose we can check with one of those sequences whether the M infinity has scalar greater than 0 using this limit. So then what happened is that Basilio Dajic and I decided to sew tunnels along a curve. So you have an S3 here, and we cut out, so for the first term in our sequence, we cut out 2 balls, and we take 2 half Schwarzschilds here, and then we glue this ring to this ring, so that this purple path starting here can run through this, jump over here instantly, and come out. So that makes the distance between these 2 points quite small. Other distances will be along the sphere. In the second step, we have 4 holes cut out, and we attach these 2, and then we attach these 2, so that a purple string coming geodesic from this point to this point will go through this hole, then it comes out this hole and comes in, and then it comes out here. All right. Notice we do this in a sewing pattern where you make a large stitch and then a small one and then a large stitch. If you evenly space the holes, we don't actually end up having the lengths between these 2 points going towards 0. But if we do it in this pattern where we have a big space, short space, big space, short space, big space, short space, that's why we call it sewing, we do increasingly many, we can get a limit space, taking the Gromov-Hausdorff limit, where this point goes to a line segment here where all those holes were, and then back out here. And this whole line segment has 0 length to it, because it's a limit of a lot of shortened tunnels. Is that clear? All right. We proved it was a Gromov-Hausdorff limit. We also checked, and it was the Swift. It's a Swift limit. It is intrinsic flat limit. The volumes are converging to the volumes. So this is actually converging to the sphere with a single thread here that's been pulled to a point. This thread is identified to a point. So this is just explanation. This thread eta is pulled to a single point. It's identified with a single point. So this is S3 modulo this equivalence that this entire thread eta is a single point P in the limit space. Now, when you do this, you have a limit space here, and you want to check, is the scalar curvature actually non-negative? The scalar curvature was greater than 0 for this whole sequence. What is the scalar curvature here if we use this definition to compute it? So at any of the other points, that's not actually that red point, it's the same scalar curvature as a sphere, it's 6. But if we choose this point P and we want to compute its scalar curvature, what do we get? So the volume of the ball about P of radius R in this Gromov-Hausdorff limit is equal to the volume of the tubular neighborhood of radius R around the geodesic in S3. So if you think geodesic eta sitting in S3, that has the same volume as the volume here. So we're basically taking a tubular neighborhood around here is the same as the ball. Now, if you use that volume, your volume of the ball is actually really large. It's the volume of a ball on one side, a volume of the ball on the other side, and this entire cylinder. So that means we're subtracting way too much. And when you actually do the computation, we end up with scalar p is equal to -infinity with this limit. So the answer to Gromov's question on some level could just be no. It's not true for these notions of convergence. But maybe some other properties of scalar curvature persist under these limits. And as Gromov responded to this example, he said that, well, in fact, this definition for scalar curvature has been completely useless and was never applied to get anything useful about scalar curvature. And that's basically true. Nobody ever used this definition to prove anything. So we should look at what other properties of scalar curvature there are that we could examine. But I have to admit, I've just added in another slide since yesterday with another example, because people were asking some more questions about constructing sequences and what sort of limits they could have. So I'm going to show you, before we discuss other properties of scalar curvature, I'm going to show you some more examples. So we have the same idea of we're going to be cutting holes and making tunnels. And remember what our tunnels all look like. I'm just going to go back to remind you. They all look like this piece when they're actually connected. So let's see what can happen if we connect them in a different way. So now, in this case, let's picture a sphere. We're going to make an example with scalar greater than or equal to 0. The volume is going to converge to twice the volume of the sphere, and their Swift limit is going to be the 0 space. So I was mentioning this one yesterday. So we have a blue sphere here and a black sphere inside. These are both three-dimensional spheres, and they're roughly the same size. And now what we're going to do is we're going to remove balls from the blue sphere. So I cut out all these blue balls here from the blue sphere. And then I'm not going to glue them together. Instead, I'm going to remove balls from the black sphere. So I have all these purple balls here that I've removed. And then we're going to make tunnels between the blue sphere and the black sphere. So we put tunnels all over it. And this space now is a new way of gluing together two spheres in a different way than has been done before. And all those tunnels are going to be made very, very dense and very, very tiny. So we get this sequence here, 2 tunnels, then we have lots of tunnels, and we have more tunnels. And the Gromov-Hausdorff limit will be an ordinary sphere. It won't be 2 spheres anymore. The 2 spheres will have been glued completely together. And the way you can see this is you can sort of see how the distances between points here that on the one sphere are getting very close to the corresponding point on the other sphere, just running through one of the tunnels. They're not close over here. In this picture, he has to run all the way over here through this tunnel and back. So these, in this first picture, these 2 corresponding points are not close at all. But as the tunnels become more and more dense, one point on the one sphere and the corresponding point on the other sphere become very, very close. And in the Gromov-Hausdorff limit, it's just a single sphere. But in the intrinsic flat limit, it is 0. And the reason it's a 0 space is you can take these sequence of guys and you can put them into metric spaces Ej, and you can fill them in with volume of 1 dimension higher that is actually going to 0. So the volume between these is getting very small because these are becoming very, very dense. All right. Now let's take almost this exact same example, and we're going to do a twist. If we twist each tunnel and glue them with an orientation flip, then the 2 spheres do not get close to one another. They're having the wrong orientation and they don't fill in with the B. And in that case, the intrinsic flat limit is an S3, but the weight is 2 everywhere. So that's another example done with scalar greater than or equal to 0 using this tunnel system. Then there's another thing that one can do. Sorry for the parentheses here. We could take an increasingly dense collection of balls in S3. So here's an S3, and I'm going to connect points in S3 to itself. But I'm not going to sew it. I'm actually going to connect them with tunnels from this point here to this point, a tunnel. If I have 3 balls, I connect every single ball to every other single ball. So if I have 4 balls, this guy has 3 tunnels going to the other balls. He has 3 tunnels going, and we keep doing this. Now, imagine that these tunnels are short, though, okay? So if you imagine that these tunnels are short, I just drew long lines because, it's easier to see what's going on here. then every single pair of points has run a tiny short tunnel between every single ball and ensure the total volumes of the tunnels goes to 0, then those tunnels are not contributing to the intrinsic flat limit. The limits, the Gromov-Hausdorff limit will be what? What do you think it would be? I mean, the distance from, say, this point to the other pole would be run over the nearest ball, go to the nearest stop here, and come up. So think of this almost like a subway system or something that just has every trains between every pair of stations. Every single point on this entire sphere has a quick route to the other point. So the Gromov-Hausdorff limit is a single point. We've just collapsed the space without any collapsing. There's no volume going down. The volume is actually converging to the volume of the sphere. But the Swift limit will be 0 because the Swift limits are always subsets of the Gromov-Hausdorff limits, and the Swift limits have to be 3-dimensional, and the Gromov-Hausdorff limit is 0-dimensional, so it has to be the 0 space. Again, this is done with positive scalar, and each one of these tunnels looks like a little Schwarzschild. They just look long here. We could also just limit ourselves to balls in a domain U so that we only make a single domain get squished to a point. So then the Gromov-Hausdorff limit will be S3 modulo U, where U is this open set in S3 that's just identified to a single point. And so we consider this pulling a whole region to a point. So that gives us more examples where you can imagine any sphere, a possible limit is take various open domains sitting inside the sphere and identify them to single points. Even if they're not connected to one another initially, they can be connected later. And this gives you a very wide variety of possible limits, Gromov-Hausdorff and Swift limits of manifolds with positive scalar curvature. Remember that to have this Gromov-Hausdorff limit, these are not actually long tunnels. When they're long tunnels, there wouldn't be a Gromov-Hausdorff limit because then there would be two. This would not actually be close, right? And there would be too many midpoints of too many balls inside. The number of balls in the space would go to infinity if these were long tunnels, because there would be balls centered at the midpoints of these tunnels. But because these are short tunnels, they just look long, we do have a Gromov-Hausdorff limit. But the next thing we thought about is, well, maybe we can make long tunnels between balls. So this is work with Basilio Cazares. And now we have the same picture, but instead, every one of our tunnels has made to have the length d inside Euclidean space of dimension 4 between P and Q. So think of S3 as sitting in Euclidean space dimension 4 and make the tunnels have the length equal to the distance between the 2 points. So now I want everyone to consider, what do you think might be the limit of this? Is there a Gromov-Hausdorff limit? And is there an intrinsic flat limit? Each tunnel has a little bit of Schwarzschild and a long cylinder and a little bit of Schwarzschild. I mean, that's the way I'm having a geometric think about it. In the paper, we actually smoothly make it very clearly positive using work of Dodger. So this is as long as the distance in Euclidean space between each of these. So it's not going to have a Gromov-Hausdorff limit because we're getting increasingly many tunnels of length 2 in this manifold. We're going to, as more halls, there's going to be length 2, 1 here, length 2, 1 here, length 2, 1 here, length 2, 1 there. Many tunnels of length 2 would make increasingly many points needed to create a net of diameter 1, radius 1. So this does not have a Gromov-Hausdorff limit. However, if you guarantee that the total volume of the tunnels goes to 0, so you have to make the tunnels really, really thin to do this. Okay, again, we're taking advantage of Schwarzschild space having a parabola effect, so we can really make it very thin by rescaling. So we ensure the total volume of the tunnels goes to 0, then the tunnels are not contributing to the intrinsic flat limit. And we are able to prove we construct a Z, explicitly construct a metric space Z between this and the limit space. The limit space is actually S3 with the Euclidean distance, which is a space that has no geodesics at all. It has no geodesics in the sense that if you have 2 points, there is no midpoint between those points. There is no geodesic curve between those points whose length is the distance between them. The distance between the points is the straight Euclidean length, which doesn't run along the sphere. So I was wondering if anyone has questions of other examples that can be constructed or want to ask more questions about this before I continue, because I'm not going to do more examples in this talk. All right. The examples in these papers are all done on S3 just for ease of use. S3 has strongly enough positive curvature and it's constant, and so we can do things, but you can actually do things where you deform your manifold slightly to have little bits that are positively curved and just glue at those spots. And you can do quite a variety of different manifolds. So this process is leading one to expect that it's going to ruin any kind of scalar curvature on the limit space when you don't even have the limit space looking remotely like a Riemannian manifold. It doesn't even have geodesics inside it. Even though it's a connected limit and it doesn't have geodesics. This starts to become troublesome towards trying to define properties of limit space. All right, so let's go now to properties of limit spaces. Properties of scalar curvature, and see if some of these other properties hold on the limit spaces, even though the volume limit doesn't. So there's this notion of stable minimal surfaces in M3 with scalar greater than or equal to 0. So a surface sigma 2 inside M3 is a stable closed minimal surface if it minimizes area of any continuous deformation sigma t. So it's closed, it doesn't have a boundary. And I deform it, and I'll make the area larger when I deform it, or equal. So here is inside a torus, this is a 3 torus. There's a 2-dimensional torus here, and he's stable. If I deform him, his area either gets larger or it's exactly the same. If I deform him equally all in one direction, parallelly, then yes, it's exactly the same, but most deformations will make it larger. And this guy, no matter how I deform him, he will actually get larger, strictly larger. So this one's a strictly stable minimal surface, and this is just an ordinary stable minimal surface. And we don't have boundary for these guys because he's closed minimal surface. So I'm not going to actually have a boundary for these 2 pictures. Shane and Yao proved that if G is a C2 Riemannian tensor, then by taking the second variation of area for these sigmas that are stable minimal surfaces, and when you take the second variation of area, you see a Ricci curvature term, and you can balance it out and have the scalar come up and another term come out, and you work it out. It's a very nice argument. And then they apply Gauss-Bonnet to the surface, and they are able to show that the only stable closed minimal surfaces in M3 with scalar greater than or equal to 0 are tori and spheres. So the other genuses don't happen. And this is the only example with tori is something like this, and here's an example that's a sphere. Now this is a picture of a 3-dimensional sphere with positive scalar curvature. This is one of these Schwarzschild style necks, right? Running between a small sphere and a big sphere. And we see there's a minimal surface, a strictly stable minimal surface in here that is a sphere. This is, by the way, also a minimal surface. It's unstable. About every point in here, you can have a small little ball intersecting with it, and then it will have boundary, and then you can check and it will be minimal. But globally, this guy is not minimal. He's unstable. And this one's similar. He's not globally stable, but local perturbations will be minimal. So these ones are called minimal surfaces, but they're not stable. Shane and Yao proves this torus rigidity theorem. It says that if M3 with scalar greater than or equal to 0 is homeomorphic to a torus, then M3 is isometric to a flat 3 torus. So that this picture here is actually the only possibility, well, all different widths and lengths to this torus, but they're always a flat three-dimensional torus if you actually have scalar gradient to 0. So it follows combining this with much more work, okay? It's not just an immediate consequence of this Chain-Yau theorem about minimal surfaces, but you can sort of see the picture here. There's something going on when there's a stable torus inside. So it's natural to ask, does torus rigidity hold on M infinity if the scalar MJs are, we don't assume that they're greater than or equal to 0, we assume they're greater than or equal to -1/j. So they're sort of moving up towards being greater than or equal to 0. So this is another question Gromov posed. And now the examples I talked about before don't quite work because you can't just attach tunnels to something that isn't positive. But we have work to appear where we're sewing to doing a sewing on tori with a curve going towards a point, and the way we're doing it is we're using the fact that there's this flexibility of -1/j to give us a little bit of a negative up, and then we create little pieces of spheres, and then we can make tunnels on those little pieces of spheres. So this is to appear, and I don't want to give too much details because it's not on the archive yet. But the idea is to do this kind of sewing process with a -1/j factor onto tori. So you start with a flat torus, you make it a little bit of a negative, it gives you lots of little lumps that look like balls inside spheres, and then inside those balls, you will construct the tunnels. And in that process, we'll be able to have a string pulled to a point. Now, if we do that, then it would be saying torus rigidity doesn't seem to hold because we would have a limit that's a torus with a string pulled to a point. That's still homeomorphic to a torus. The string pulled to a point doesn't ruin that it's homeomorphic to a torus. You could also pull a ball to a point. You know, using the same idea I mentioned before, we could take a region U and make that whole region pull to a point. So we would then have examples that show that torus rigidity isn't working either. All right, so here's another property of manifolds with scalar gradient to 0. Gromov and Lee showed that if M3 has scalar gradient to 0, and then any cube P3 contained in M3 satisfies prism rigidity. So what is prism rigidity? Prism rigidity says that if a face inside P3 is mean convex, so that means it's sort of bowing outwards in an average way, so that if you deform the area of a piece of it locally, the area, if you deform inwards, will decrease. Okay, so that's what mean convex is. Of course, it's defined with second derivatives, but I'm sort of giving you a geometric intuition for it. So area decreases if you go inwards, but area would increase if you go outwards. And at any point P lying on an edge of E3, an edge E, so here's an edge, here's a point P, the dihedral angle theta P is less than or equal to pi/2. So it's saying that these angles here are all going to be less than pi/2. Then P is isometric to a rectangular prism in Euclidean space. So let's just go over the definition. F is mean convex if local inward deformation sigma t have area sigma t less than or equal to area sigma 0. You have to define these local, maybe a better definition would be local outward deformation have areas increasing rather than this one. This is actually not so great. You have to be more precise as to what kind of your inward deformation should be. And the dihedral angle at P can be defined using volumes. You could say, okay, I'm going to figure out the volume of a ball about P intersected with the prism. And that volume compared with the volume of a ball in Euclidean space, this ratio should tell you, when you multiply by 2 pi, the angle of what percent of the ball is inside the prism, which is roughly the dihedral angle once you take a limit. All right, so this is defined in a geometric way. And so you can ask, Does prism rigidity hold for cubes in M infinity if scalar mj is greater than or equal to -1 over j? All right, so there are no examples related to this question. It's an open question. If somebody wants to try to make such examples, we might try to possibly be able to get at some using the same idea we're using for the tori. So it's possible that will also fail, but this is another key property that Gromov has defined as being crucial towards what would be a natural scalar non-negative property. This property is closely related to torus rigidity, and you can sort of go back and forth between this and torus rigidity. One way to see this is if you reflect across each of these sides, you can build a torus out of a prism. If you have this prism and we reflect across these sides, we get a non-smooth torus. So if I reflect this across the side, that means that this side can glue to its reflection all the way over here. And if I reflect this up, the bottom can glue to its reflection up there. And I also reflect forwards, so the back can glue to the front. And what we end up with is 1, 2, 3, 4, 5, 6, 7, 8 copies of this prism, but now the sides can be glued. It's not a smooth prism anymore. All 4 sides can be glued. This is Gromov's approach to discussing this. You have 8 copies of your prism and you're gluing the opposite sides to each other. Then you smoothen it a little bit and it still has non-negative scalar because the mean convexity, you can deform it to match, and then he has an argument how to deal with the edges as well. I'm not going to give his full argument. It's sort of hand wavy and beautifully geometric, but I'm not going to give the full details here. But the idea is he makes a torus out of it. And then he says, oh, torus rigidity, therefore this was rigid. So that's sort of a geometric intuitive proof of why this rigidity theorem holds. The fact that P is isometric to a rectangular prism in Euclidean space. Now, Chow Li has a beautiful proof where he proves this theorem using capillary effect. And instead of minimal surfaces, he uses capillary surfaces, which are surfaces that have a little bit of pressure on one side, and they are forced to attach to the edge with certain angles. It's sort of like water filling a glass. It has a little bit of a curve to it because of the effect of water meeting the boundary of the glass. So he uses the capillary flow, and he uses a kind of second variation argument similar to Shane Yao, and is to show the properties of how this flows forward, and he's able to prove this prism rigidity in that case. All right. So again, these theorems are all about minimal surfaces and how minimal surfaces are behaving, or how constant mean curvature surfaces or mean convexity, these kinds of behaviors seems to be more useful toward proving results than the limit behavior of volume of a ball. But the problem is that all these theorems are based on the idea that we have a metric tensor G, and we can take 2 derivatives of a metric tensor, and we can define Ricci curvature before we define scalar. And you're kind of using the Ricci curvature to get these second variations. And it's completely unclear how much this is even true in Finsler spaces, which don't have the metric tensor that's an inner product. All right. Then there's another very interesting property involving minimal surfaces and scalar curvature. There's this thing called the width. So the width of a manifold is the infimum of the areas, infimum over all sweep outs. So a sweep out of sigma t of m is a collection of levels. That's a family of levels of a function that's been pulled over by a diffeomorphism. So just sort of picture families of levels going around from one end to the other end. Family of diffeomorphisms pulling back a level sets. So families of ways of deforming from a single point, open up around spheres, 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 and close to a point again. And it doesn't have to stay as spheres. These do not have to be smooth levels. They can change shapes. The family of diffeomorphisms, you sweep out from one end to the other. And then for each one of these sweep outs, you look at the soup of the area, the biggest area for each sweep out. But then you take the infimum over all sweep outs, and that gives you the width. So this is the width for this shape. because the best sweep out would start here and go to there and go around the, if I tried to start here and go around this long way, I would get a bigger maximum area. So that wouldn't be the infimum one. So the width is the smallest of the maximal areas needed to sweep across the surface. And in the sphere, it's the equator is achieving this width. The width is achieved by a minimal surface, and the minimal surface may be unstable. The width of a sphere is 4 pi achieved by the equatorial S2. Does anyone have more questions about the sweep outs? Okay. So Marcus and Nevis proved that if M3 is diffeomorphic to a sphere and has scalar gradient equal to 6, and the width of M3 equals 4 pi, then M3 is isometric to a standard sphere S3. So this has a completely different proof. They can't use the stability of minimal surfaces because it's actually generally an unstable minimal surface. And the proof involves Ricci flow. And again, one can ask whether this theorem is hold if you have MJ that's a limit of M infinity, which is a limit of MJs with greater than equal to 6 minus 1 over J. Now this is, I have a chat. Yes, let me see. What is H in the definition? Yeah, H is something like a height, say. So imagine that if it's a sphere, for example, you could think of the standard sphere and H would be the Z coordinate. And then you want to look at all diffeomorphisms on the sphere and the pullback of that. And if it's a different M3, then H could be similarly something defined globally in that way. The proof uses Ricci flow, and they have ways of controlling scalar curvature under Ricci flow. Scalar satisfies an actual differential equation as it changes under Ricci flow. And they can also keep track of what happens to the width under Ricci flow. In fact, there's an earlier paper of Kolding and Minicozzi which uses width to better understand Perelman's proof of the Poincare conjecture. So they explain the end play of his proof for the Poincare conjecture in particular using width. And so it turns out this width interacts very beautifully with Ricci flow. So now you might say, okay, well, that's interesting. That's a new approach to understanding about positive scalar curvature, but Ricci flow, once again, is using Ricci curvature, which is using a metric tensor. That is, in fact, an inner product, not just a norm, and it's using a lot of power of Riemannian geometry that may not carry over to metric spaces or not, but you are, in fact, watching a series of talks by Bamler in the afternoon concerning Ricci flows with weaker hypotheses on the manifold. So then it becomes natural to ask to what extent is scalar sphere rigidity going to hold if you have a weaker metric tensor. It's still a metric tensor, but maybe it's only C0. Right. Okay, so now we want to say which some of these three main ones, the torus rigidity, the prism rigidity, and the scalar sphere rigidity theorem, which of these three would hold on a limit space, but maybe we should consider all the different possible limits instead of just Gromov-Hausdorff. We were seeing that maybe these don't work for Gromov-Hausdorff or not. So let's just look over the different kinds of limits again. If we have CK convergence, then it definitely is going to hold in the limit space. So this is just a review. You've seen all these definitions before. I'm just using this as a guide to have our discussion. We know the CK convergence is examples like this. Under C2 convergence, you definitely have The metric tensors converge to the metric tensors. The Ricci curvature converges to the Ricci. The scalar converges to the scalar. Every single step of a Ricci flow converges. Every single step of what is a minimal surface converges. So these are very straightforward. C0 convergence, now it becomes far more difficult to talk about what would happen. You can have cones tips develop. You don't have the, you do have a metric tensor. That's a great plus. But is that metric tensor smooth enough to do any of the minimal surface theory? Maybe not. And then we have this VADB convergence, where you have volumes and distances. Now, despite the fact that C0 convergence is not immediately obvious that anything should work, Gromov has proofs and Bamler have proofs, and Burkhard Gwim, who's speaking next week, have theorems about scalar curvature properties persisting under C0 convergence if you assume the limit is also smooth. So they forbid that there's a corner. There may be newer results that I haven't seen yet, but they are working on the C0 setting where they assume there's a smooth sequence and only C0 convergence, but then, oh, luckily it's smooth at the end. One can get that the scalar curvature of the limit space is smooth too. Sorry, the scalar curvature is positive on this limit space, and then you get all the results to work. And they're working to further improve these results without assuming smoothness on the limit space. So if you attend Bamler's talks, you are going to be learning techniques, Ricci flow techniques that you can use on limit spaces with only C0 metric tensors, and see if you can prove some of these theorems. Now, I have to warn you, Bamler and his students and postdocs are working on this approach. So you have to check with him whether the project's already being worked on. For a volume above, distance below convergence, this is a newer notion. And now we've weakened it further. We only have the volume converging above and the distances from below. And now it's a completely open question. What can one do? And it would be interesting to combine the techniques that Bamler is teaching in the afternoons to see what could you maybe get out if you only have this kind of convergence. Do you have anything you can discover about Ricci flows? Is there anything you can learn in that setting? Now notice, these VADB convergence, all those examples, all those bad examples I had with the tunnels, with the sewing, with the tunnels that are long and thin, all those different tunnel examples do not converge in the VADB sense, because volume above, distance below convergence has a C1 diffeomorphism between the two. So it doesn't allow increasing topology in the sequence. So it can be hoped that everything that's been proven for C0 convergence, which many results have been proven, could be proven in this case too. There are no counterexamples yet. All right. So this is some of what I just said, that if MJCK is due for K equal 2, we have second derivatives for C0. They all hold if MJC0 to M infinity is smooth. The proof is by Gromov using prism rigidity and also by Bamler using Ricci flow. He shows the prism rigidity theorem persists, and he's able to show that the scalar from the prism rigidity, he can get the torus rigidity. So let me just talk a little bit about this. Scalar greater than or equal to 0, he shows this if and only if prism rigidity holds for all cubes. So tiny cubes. Prism rigidity property persists under C0 convergence is Gromov's next step. And then the limit space has prism rigidity for all cubes, so therefore it has scalar greater than or equal to 0. So those are the two big steps that Gromov proves. And I wanted to mention this a bit more because these are the two key steps you might want to look at for any question. Relate scalar non-negative or scalar greater than 6 to a property. Then make it an if and only if. The way this goes backwards is because you can use tiny cubes. So you take a property, you make it local, prove it one way, prove backwards, then show this property persists. The property should be something that doesn't involve limits or derivatives because you want it to persist on all scales. And then you should have the property on the limit space, and you say, well, if the limit space happens to be smooth, you can use the first step again to get scalar greater than or equal to 0. If the limit space is not smooth, you can use this property to define non-negative scalar curvature. So you say that's generalized scalar curvature. Let me just relate this to something you've been learning in the mornings with Ricci curvature. You have Ricci curvature non-negative if and only if you have the RCD properties that you've been told, right? So you have Ricci non-negative if and only if you have the RCD properties. That's the theorems that was mentioned by Mondino in his talks. So that's an old one, an old theorem. And then they proved that under measured convergence, the RCD property persisted. And so then if the limit space happens to be smooth, the limit space has Ricci non-negative. So therefore, if you have a sequence of MJs with non-negative Ricci curvature, and you take a measured Gromov-Hausdorff limit, the limit space happens to be smooth, then it has non-negative Ricci curvature. If the limit space is not smooth, then you define generalized non-negative Ricci curvature using the RCD properties. So it's the same concept being again proposed here and actually successfully used with C0 convergence. But we would like to extend it to more notions of convergence because C0 is perhaps less natural. Badler has a Ricci flow approach where he takes your sequence MJs, C0 to M infinity, he flows them a little bit, Ricci flows at M infinity, Ricci flows at MJ, shows that the Ricci flows converge better than C0. And he's able to use the scalar curvature on the flow, moves over to scalar curvature later, and then back up. Right, I hope he does talk about this a bit in his afternoon talks. What if M infinity only has a C0 metric tensor? This is open. You can see recent work also of Burkhardt-Gwynn using Ricci flow to try to extend this idea and make a, well, actually, I wouldn't say try, successfully showed that you can define non-negative Ricci curvature using Ricci flows of C0 metric tensors. So she has a Ricci flow definition for non-negative scalar on a C0 metric tensor space. And Gromov is using a prism rigidity for a definition. So there's two different approaches to generalizing non-negative scalar. It's an interesting question to say whether these two agree in some sense. And it's completely open if they hold, if you have volume above distance below convergence from MJ to M infinity. If you assume M infinity is smooth, could we get this prism rigidity effect? Can we get the Ricci flow effect? Are we able to show non-negative Ricci curvature on non-negative scalar curvature on M infinity? That's completely open. So that's one of the open problems that someone here might want to work on because you're having the opportunity of hearing Bandler's talks as well. So you're going to learn the techniques that they have. Burkhardt-Gwynn was Bandler's student, graduated already, but was Bandler's student. So this is a good opportunity for someone who might want to look at their techniques and apply it in a larger setting. Are there any questions? Yes.
Yeah, it's Andrea. Just one curiosity. So this prism rigidity for all cubes. So this is for a smooth metric tensor, and how how one might hope to extend it to a metric setting, say, or say a very low reality setting as a definition of
yeah, so let me go back here. So I'm going to give credit to Gromov for this. This is, I think this should say locally outward. Okay, but if you define mean convex in this way, that doesn't require any smoothness.
Right.
Just areas. And dihedral angle here, this is only involving volumes and distances. So it's volumes, distances, and areas. Okay. This is a volumes, distance, and area definition of being a prism, of being a cube that satisfies its properties. And then you would say that anything that has these properties must be a flat rectangular prism from Euclidean space. Well, that's also defined for a metric space, being isometric to something like this. Right. So this definition, like this is proposed really by Gromov. I think this should say outward, but anyway, outward and greater and equal. That every local outward. See, so this is interesting because this is defined actually on a very large class of spaces.
Right.
The so dihedral angle, on the face of it, a dihedral angle could have involved having a and Hilbertian or an inner product, but this is not an inner product definition.
Right.
So this is quite intriguing.
Yeah.
Yeah.
And when you say for every prism, you mean that you're considering basically a partition, a partition of your space in a small and
No
smaller-
partitioning. Given
No.
any point,
Mhm.
if there exists, if at every single point, if you
Mhm.
could make a cube about that point that satisfies these two conditions, then it has to be a flat Euclidean prism.
Okay, got it.
In other words, they may never exist and there might not be any, and that's natural, right? Like a sphere
Mhm,
has
mhm.
none. A sphere has none. So having none is the thing. Yeah.
Okay, thank you.
Yeah, it's kind of interesting. But Lee's proof that this holds on smooth Riemannian manifolds is in some sense the only actual proof in the smooth setting. Gromov has his Gromov style proof that I mentioned, where you glue them above and below and all that and turn it into torus rigidity question.
Mhm.
The proof of it is using very much second order deformations of second order, the second order derivatives of the metric tensor. So the proof is still very smooth, but the statement now, this statement is a conjectured notion of generalized non-negative scalar curvature, which is actually beautifully easy to state. It would be interesting if you want to check if this holds on RCD spaces. But I wouldn't say that it's an open problem that I know is open in the sense that I don't know if someone's already working on this. Because Gromov published this a while ago. This is not new.
Mhm.
It's just that Lee's proof is very new. Lee's proof is the past 2-3 years. So some people were ignoring this until they saw the Lee proof.
Okay, thanks.
Yeah. Any other questions anyone has? A Babler may mention more about his Ritchie one. It's my understanding that him and Burkhard Gwim have do need the metric tensor and do need it to be C0 metric tensor to define their scalar. But this one is very, very low regularity. Yes.
I was wondering if what would be an example of a sequence for which there is no C0 convergence, but for which there is VADB convergence?
Yes. Actually, a lot of these, but wait, VADB is, wait, sorry. I think I went further back before than I thought I had. VADB and no C0. This one here. And also the Ilmanen example. So for
All right.
VADB, you can tuck your phi j's are still, they're still diffeomorphisms. But you see how much this has been stretched out. So the diffeomorphism goes from here to here. The diffeomorphism is stretching. It's only bounded below by the distance in the limit.
Okay.
And the volume's coming down. So this sequence and also the Ilmanen ones with lots of wells have VADB. So it has an interesting thing to say, I want to study the VADB, not just the C0, because the Ilmanen examples have been considered so important for so long. And it would handle those. Also, anything that fails for VADB will fail for Swift convergence, right? This is a test case that's testing the larger class of examples. All right. All right, so if you have CK, everything works. If you have C0, this, and you assume the limit space is smooth, you have the prism approach and the Ritchie flow approach. And if this limit is not smooth, you still have this prism definition. It still holds on this limit space. And there are, Burkhard Gwim has a Ritchie flow definition for non-negative scale on this limit. It would be interesting to check which pictures would be nice to look at just to get a feel. That hasn't been checked so much. And then the VADB approach, this would be interesting to look into also. What happens under Ricci flow? One thing people can look at is just assume it's a work product. And so it just has one well. Just look at that case, a sequence with one well. See what happens to the Ricci curvatures. That's would be interesting to look at already. And you can ask Bamler about it in the afternoon because he may even know, he may have a geometric understanding with this particular picture and give some sense. All right. So let me see. I think I said this. I said this. Yes, I passed here. Here. Okay, so that was the question. If M infinity is smooth, can you extend some of this work or do something different? And now here are all sorts of projects that you can do. Investigate the following rigidity theorems to see if it holds on smooth M infinity where MJ VADB to M infinity. So many of these will be already known for C0 convergence because of the work of Bamler and Burkhard-Le Guin, but now you can try to see if they work in general. So there's a scalar torus rigidity theorem, Shane-Yao, that I already told you, prism rigidity and the scalar sphere rigidity. There's also a minimal torus scalar rigidity theorem of Tsai-Galloway, which talk about how the minimal torus achieving certain things must force the minimal torus to have a certain isometry to it. There's a hemispherical scalar rigidity theorem of Eichmeier, which is similar to the scalar sphere one, okay? So it has certain list of properties and it's forced to be a hemisphere. So it's a boundary version. The cover splitting rigidity theorem of Bray-Brendel-Neves. This is a theorem which forces that there exists a cover that is R isometric splitting R cross something. And the RP3 scalar rigidity theorem, which is very similar to the scalar sphere, but forces it to be RP3 exactly. These ones are using Ricci flow techniques. And then there's the zero mass rigidity theorem of Shane and Yao. Now, that's part of the positive mass conjecture. The positive mass, sorry, it's a theorem now, but everyone still calls it a conjecture. What? I'm old, okay. The Shane-Yao positive mass theorem says that if you have an isolated gravitational system, so you have non-negative scalar curvature on a three-dimensional Riemannian manifold, and asymptotically it's flat, just like that asymptotically it's flat towards infinity, and you can check second order behavior towards infinity, and this is related to the Schwarzschild space having the same behavior, and it has a mass, which is the mass of the black hole, the Schwarzschild black hole, which is related to the area of that neck. You compare a space with scalar non-negative, similar to Schwarzschild at infinity, and you say that the mass has to be actually non-negative if the scale is non-negative inside. And if the mass hits zero, then the entire manifold is Euclidean space. So if there's no mass in a region of space, then the space is flat. That's basically what it's saying. And so you can call the zero mass rigidity. And there are many results towards proving that the zero mass rigidity holds. This is the most well understood one here of all the theorems that we've talked about. The most work has been done in this direction on these problems. And the zero local mass rigidity is Schur-Tamm have a local mass theorem that says if you have a region that's convex, then you can find the mass of the region, called the Brown-York mass of just this region. And if that mass is zero, then the region is flat. So these two theorems are actually perhaps more studied than any of the rest of this, because this is so important to people to understand the almost rigidity of these for physical reasons. Okay, so let's note, if a rigidity theorem requires scalar of m is greater than or equal to h, when you look at all of these rigidity theorems, this one's been written up, okay, but everyone else has really not been written up that much. Note that if the rigidity theorems require scalar m greater than or equal to h, then you study smooth M infinity where mj is converged to M infinity with scalar mj greater than or equal to h minus 1 over j. What you want to do is look at the case of VADB convergence to sort of test whether these theorems have a hope of still holding on the limit spaces. Which of these theorems should hold? This zero local mass rigidity theorem of Schur-Tamm, this would actually be about as useful as the prism rigidity theorem, because this is saying, oh, if your local mass is small, which is something measuring the behavior of the mean curvature on the boundary of a region, it forces that if that mean curvature is too small, then the inside is flat Euclidean. So this one actually is an if and only if statement. It says that if your scalar non-negative, if and only if the zero mass local mass rigidity holds for all small neighborhoods that have convex boundaries. So this one is another one that's a candidate for looking at as a first step of those two pairs of steps. This has not been looked at much yet, so it would be interesting to check it for VADB convergence. Okay, all of these conjectures are talked about in this paper, which I don't know if I linked to it in the chat. I'll link to it in the chat after the talk. This paper here discusses all the conjectures we made at this meeting, and we discussed all of these various ones here. All right, there's much more discussion of these two, but I didn't think I had that much time in this conference to talk about these two, since ADM mass and mass is not well known to the non-physics audience. This is the general relativity audience is very interested in these two. All right, so now people say, do the scalar rigidity theorems hold for volume preserving intrinsic flat limit spaces? So as I said, that there are non-examples, right? There's GH and VF converging sequences made out of the sewing that didn't work, but they have the topology increasing. So they're not counterexamples for the volume above, distance below convergence. But also notice, and this is perhaps a stronger thing than saying the topology is increasing, every single tunnel contains a stable minimal surface. There's a stable minimal surface in here. And there's stable minimal surface right here where they're glued. And there's tinier stable minimal surfaces. So these non-examples, all the different kinds of non-examples I presented, had tiny stable minimal surfaces. If we had more tiny stable minimal surfaces, then min A of MJ is going to 0 for this, where min A is the minimum area of a minimal surface. So this min A condition becomes a natural condition to add to try to get rid of the non-examples. So you can say, do the scalar rigidity theorems hold on limit spaces if we assume MJ VF converges to M infinity with min A of MJ greater than equal to A greater than 0. So we add this condition to volume preserving intrinsic flat, and we ask if the scalar rigidity theorems hold on such spaces. Now, all the sewing examples and all the tunnel examples are no longer allowed. They don't fit these hypotheses. The VADB examples fit these hypotheses, so they are a good test. And we've eliminated all the known non-examples. So now you, of course, have the approach. You can say, can I try to find a different kind of non-example, right? And I should point out, and I didn't put it in here, but Nabler, Lee, and Neumeyer have a paper, and they have some non-examples in dimensions higher than 3. Okay, so their dimensions start in 4. They have an interesting sort of pulling effect where you can pull a geodesic to a shorter length, not all the way to 0, but to a shorter length, I think. And they don't need tunnels to do it, but they need dimension 4 and up. So there's no known non-examples in dimension 3, except ones that involve tunnels. So it's an interesting question to try to find new examples. And everything here is 3-dimensional, all these conjectures. So let's talk about VF geometric stability conjectures. So geometric stability conjectures are stronger than the conjectures we've been talking about. A VF geometric stability conjecture states that if a manifold which almost satisfies the hypotheses of rigidity theorem must be VF close to a rigid manifold that satisfies those hypotheses. So let me just state the conjectures. Geometric stability of a Taylor torus, this is stronger than saying, does this property hold on a limit space? Okay, it's saying that if you're not on the limit yet, you're close to a limit which is exactly that torus, or is exactly a prism, or a flat prism, or is exactly a sphere. And one method to prove these is you directly estimate the volume of the manifold. You directly estimate the Swift distance. That's one way to prove these kinds of theorems. And that's primary way people have done. And on lectures 3, I'll talk to you how you can start directly estimating swift distances between two manifolds. And that's done in special cases. A second method is to prove these, is to use the IAS scalar compactness conjecture to show that a subsequence has to converge in the volume preserving intrinsic flat sense, and then prove the rigidity theorem holds in the limit. So when I said, oh, one of the open questions is to try to prove rigidity theorems on the limit spaces, that's like part of this process. You prove the conjecture, and then you prove the rigidity theorem on the limit space. Or you do the direct estimates. This is the easier method. And there's lots of methods for trying to directly estimate the swift distance. However, it seems to only be workable so far in special cases. So for the big overarching open question that may take a decade to solve for these, solving this in full generality would take a decade. This conjecture would be a key step, and then proving the rigidity theorem on the limit spaces. Okay, all of these, when we make them have the hypotheses, we add the min A, mj to the hypotheses of our geometric stability conjectures, because otherwise we have all these non-examples. So let me go over that compactness conjecture that I just said we might use as a first step. I just want to go over it one more time. We mentioned it before. Suppose MJ3 have volumes less than or equal to V and diameters less than or equal to D. Then we know by Wenger's compactness the subsequent swift converges, possibly to zero space. We know that the limit for the volumes is bigger or equal to the mass, or sort of a volume of the limit. And we know that if the limit is not zero, it's at least M rectifiable. It has charts, it has weights, lots of nice things about it. The conjecture is that if in addition we have scalar gradient to zero and the min A's bounded below, then we have VF convergence, not just swift convergence, but also the volumes converge. Okay. And the limit space should have some generalized notion of non-negative scalar, which could be one of the notions we just described. What properties of scalar curvature are conserved when we do this VF convergence with min A greater than or equal to zero? This is the ultimate challenge here. We haven't even written a statement of what we want it to be. That's still even open. Part of the conjecture is, what do we mean by generalized scalar non-negative? What properties of scalar curvature conserved under these would help people come up with what's the statement should be here. If you check the VADB setting, then you have an idea of what we should put here. Should we put the prism here? Well, we shouldn't put the prism definition here unless that prism persists under VADB convergence. Should we have some sort of Ricci flow definition here? Only if it also works for VADB convergence. So these are the test problems that students and postdocs can work on to help us come up with what is the correct generalized notion that we hope to work. And then for the C0 ones, I mentioned that there's Roker, Gromov, Bammerle, Burkhardt, Gwim, and others. We've already checked out the C0 case. So it's important to particularly go over those particular examples, which are cited and reviewed in that paper I mentioned, and see which ones can be extended to VADB. Sort of expect that all of them can be. If you can, you know, it's very likely. All right, so there's the conjecture again. I just have it there so we can refer to it. And then you're asking, okay, part of this conjecture is that we should be able to find a subsequence which VF converges. So can you prove a subsequence VF converges in special cases directly without using Wenger's compactness to find a subsequence? Just prove that there is a subsequence just directly itself. Okay, and actually get what the limit is. And that's actually been done by Park, Tian, and Wang in a special case. These are three students that went to a summer course I gave at the Fields Institute a few years back, and they picked up on this question of testing this conjecture. They proved the subsequence VF converges for warp products that are diffeomorphic to S3. So this is actually the only case that's been done yet. They say GJ is a dr squared plus fj squared of rg naught, where fj at 0 and fj at L equals 0. So it's diffeomorphic to S3 and it's warping in different ways. Okay, so different shapes, diffeomorphic to S3. They assume it's like this, and they take a subsequence sequence like this. They assume the volume and the diameter, the scalar, and the min A conditions. Okay, the scalar condition is actually nice ODE now. They show that there's actually an A and a B between 0 and D. D is the diameter, right? So our our work product runs from 0. This L, by the way, is an LJ. I should have put a subscript J on it. Each one of them is different lengths, but LJ is always less than or equal to D. So there exists A and B between 0 and D, such a subsequence of the FJs converges to F infinity, who's a positive function on this open interval AB, and it converges in both C0 and H1 log senses. And FJ goes to 0 uniformly on the two sides. So it could have thin wells on either side, or maybe A and B are actually 0 and D and there are no wells. But wells could develop and it will converge to 0 uniformly on these wells. They then show the volumes of these wells is going to 0, and they're able to prove that they use the Sormani theorem, which I will present in on Thursday, that the MJ is actually volume preserving intrinsic flat conversion with M infinity, where M infinity is made out of this guy, this F infinity, and he only runs from A to B. So we chop off the wells and you got this intrinsic flat convergence sequence to a guy, and F infinity is H1 log, so he satisfies this in a weak sense. So in that sense, in some H1 log weak sense, it has generalized scalar gradient to 0. It's a C0 function, so you could check now using more recent work of Burkhardt-Grimm to see if maybe this guy also has scalar gradient to 0 in the sense of which you flow. That has not yet been done. This paper is before Burkhardt-Grimm came up with the C0 definition for scalar non-negative. Their only generalized notion of scalar is this H1 log sense, which Lefloc has studied before as a scalar non-negative lower bound. Lefloc studied the the positive mass, the mass settings. We're looking at mass greater than 0 questions. Other work products are being studied by another team. This isn't the only possible work product. This is perhaps the simplest one to be diffeomorphic to S3, but there are certainly many other manifolds that could be made out of work products. And so other work products are being studied by another team, and they are checking to see if they could get the same convergence. The key idea in studying this kind of question is break the manifold, choose a subsequence where you can control which regions go into thin wells and which regions stay nice and fat. And the nice and fat regions might have C0 convergence on the fat parts, maybe, and the thin parts could go to 0. Then you can try to use this theorem that says, okay, the thin parts can be cut off and you can construct a Z and everything works nice. So that's the key 2 steps for trying to prove a special case of the compactness conjecture. You assume something a little bit more about the manifolds. You try to break it up into fat and thin parts. The thin parts will cut off and disappear, and the fat parts will converge to something that hopefully has generalized scalar non-negative curvature. Okay, so there are other work products being studied by another team. There are graph and conformal cases people can consider. A graph case would be you assume all the MJs are graphs sitting over a fixed manifold. Or conformal cases, all the MJs are conformal to one another. Does a subsequence converge in the volume preserving flat sense? These 2 cases are open and they definitely might have nice solutions. Again, you would want to break up parts that are getting thin, cut them off, and parts that are fat would remain. So we're going to go over techniques for trying to show the volume preserving intrinsic flat convergence once you actually have controls over the functions defining the metric tensors in these cases. Scalar curvature has very nice simple formula in the graph case and in the conformal cases. These are well known. So that first step of having the scalar curvature would be well known, but they will be partial differential equations. All right, so let me just talk a little bit about difficulties that might arise on that. Let me just check how much time I have. Only a tiny bit of time. So this is the scalar torus rigidity. It's stated exactly. I just mentioned slightly what it would be. Remember, scalar torus rigidity said that scalar gradient equal to 0, diameter less than scalar gradient equal to 0, and it's homeomorphic to a torus was enough to make it a flat torus. So for geometric stability or almost rigidity, we're going to add the min A condition. We force a diameter and volume from above. These 2 are needed to have the Wenger compactness theorem apply. So you'll get a subsequence that converges. The min A is going to keep it from disappearing. And so you get a subsequence that converges to flat torus. Now, why is this volume preserving intrinsic flat for this conjecture? Well, it's certainly not a Gromov-Hausdorff convergence because you can draw examples like this, which do not Gromov-Hausdorff converge to a flat torus. And you could even have bubbles. Okay, so if you don't have the min A condition, you can have bubbles forming, and you can also have those sewing examples as well. Okay, special cases of conjecture has been proven. It's the warp products, different kinds of warp products have been studied by Alan Hernandez, Parisi, Payne, and Wang. These were a bunch of students and postdocs that attended the Fields Institute lectures about this. Some graph cases have been solved by Cabrera, Pacheco, Ketter, and Perales. This is much harder. Graph cases involve partial differential equations. Remember. And conformal cases have been studied by Allen, Chu, and Lee, but they have some extra hypotheses. So you have to look into, can this be done more generally? Okay. So hopefully Perales, who's speaking next week, will talk some more about this graph case. The proof of the graph case, actually, they prove that they have VADB convergence. And then, as a result of the work of Allen, Perales, and me, the VADB convergence implies the volume preserving flat convergence. So they actually prove VADB convergence in the graph case. The warp product cases, sometimes the convergence is even stronger. So that's almost deceptive. And the conformal case, the, well, I won't describe it here. It would be interesting if Alan stopped by and talked about it here. Okay, more open cases are proposed in the conjecture on convergence of scalar. And then the stability of the scale sphere rigidity, again, remember the scale sphere rigidity theorem says scalar greater than or equal to 6, homeomorphic to sphere, and min A equal to 4 pi. The width is 4 pi, implies MJ3 volume preserving F to S3. So we're going to assume 4 pi here because the width should be 4 pi. This is actually the way Marcus and Nevis stated it. They want the min A to be 4 pi, not allowed to go towards 0, really far from 0. Diameter and volume, they said that the MJ3 should volume preserve converge to S3. This is a new conjecture. There's no partial proofs done on this. They prove, even proving the volume of MJ converges to the volume of S3 would be interesting. So just getting the volume convergence would be interesting. That hasn't been done. This is a speculative picture, but this example has never been constructed yet rigorously. Maybe these wells could be made with scalar greater to 6 minus 1 over j. It's unknown if you can do that. We know they can be done with positive, but we don't know if we can done that strongly. So show wells and tunnels can have scalar greater to 6 minus 1 over j would be a very nice open problem to solve. Special cases students and postdocs could try would be warp products, graphs, conformal manifolds. And Marcus and Nevis have a set of hints that is in this conjectures on convergence and scalar curvature that we all wrote together, and they have hints for this particular stability conjecture of theirs related to their own results. All right, so then we have the rest of the rigidity theorems. You can take any of these rigidity theorems here. You just make scalar greater than h minus 1 over j. You take your min A. I don't think it has to be 4 pi. There should be an A here. The 4 pi is needed for the ones involving Marcus Nevis. It could be just greater than A greater than 0 for the other ones involving scalar greater than 0. So some of these change what the min A should be for different settings. The zero mass rigidity of Shane-Yao, which is this case where the mass is almost 0, this has been studied in many, many cases, because as I said, this is the most important. The work has been done by Lee, Wang, Perales, Stavrov, Allen. So there's quite a few results in the direction of the zero mass rigidity. You can see summaries of all of these inside the same paper. All right, so we're done now. Lecture 1 is done and lecture 2 is done. And I think this time I managed to finish on time instead of early. Yes, it's exactly on time. So I know I rushed a little bit at the end, so please feel free to email me and ask questions now. I do want that anybody who's interested in studying any of these open questions to email me, because I have regular workshops with just groups of postdocs and doctoral students who are interested in these kinds of questions, and they work in teams on these problems. So please do email me if you're interested. Thank you.
Thank you, Christina. Are there any questions? Nothing in the chat, in the room?
No, I don't see anything in the chat.
Okay. So thank you for this beautiful lecture with lots of examples and questions. And we'll meet again on Thursday for the third lecture. Thanks a
Okay.
lot. Thank you
I will stay here in case anyone's shy to ask questions while it's recorded.
very good. Thank you very much.
Okay. All right. Thank you.